Hello everyone and welcome to this section. I'm super excited to discuss a very important technique, which we'll call it HOG features or histogram of oriented gradients, which is a very important technique that can be used for object detection, mainly in self-driving cars or any other application, which is very interesting because it will show you how can a computer, recognize a truck. We as humans, we can tell, okay, this is, for example, a truck. We can, detect, oh, it has wheels, it has specific dimensions, it has different colors and so on and so forth. That's how we can detect a truck, okay? It's very interesting to see how can we feed, a certain map, okay, within a computer that can, we can teach a machine learning algorithm to detect a truck using something that, is very difficult for humans to actually detect or use or extract information out of it, okay? All right, let's take a look. Before covering the HOG features, we're just going to talk briefly about gradients and about how to calculate gradients in general, which is kind of a basic foundation. All right, again, I don't want you guys to, that's why I didn't want to jump directly into HOG features, because here I'm just going to cover the basics of what do you mean by gradient within an image, okay? Let's take a look at a very simple example. Let's assume that I have my original image, which is kind of, all black, and it has kind of a white circle in between, in the center, okay? And what I want to calculate the gradient in the x direction, okay, which is called horizontal gradient, okay? Okay, so what we're gonna do here, we're just gonna walk from the left to the right, scan it here. All of it is black, right? So we're gonna go 0, 0, 0, all the pixels are 0. And then suddenly I'm gonna see white pixels, which indicates 255, or white color, or a bright color. So I'm going from 0, suddenly I saw 1. So that means I'm going from 0 and suddenly I went to 1, which means there's a big difference in magnitude, going from very small value to a very large value, right? So that means I can find there is a positive gradient. And that's simply indicated here in that gradient image by a white color here, indicating there is a positive gradient, okay? Indicating, okay, in this specific point, there is a change in the intensity in the original image, okay? All right, let's keep going, all right? As you move forward here, you will see you're going from white, suddenly you hit black color. So you're going from 255, suddenly you go to 0 color, okay? And that's why that's been indicated by kind of a negative gradient. You're going negative, going down. And that's why here you will see this thing get indicated by a black color, indicating kind of a negative pixels or negative gradient, okay? All right. Very interesting. Let's do the exact same stuff, but for a vertical gradient. So you're going from up down. So you guys can see here, you're gonna see there is white because you're going from black to white. And then from white to black, you're gonna see there's a negative gradient or kind of a black values here indicating negative gradient. And that's how you take your original image, you calculate your horizontal gradient and your vertical gradient. That's the first basic foundations of HOG features, okay? All right, so that's first step. Okay, what I'm gonna do with this, what's the value of it? Let's take a look. So let's take a look at an actual practical example, which is very interesting. Let's assume that I wanted to detect, for example, or obtain kind of the HOG features out of this image. The first step is, let's assume that I'm gonna zoom in within that specific pixel, which is kind of that zoom in view. And I need to represent that pixel, okay, or that kind of, kind of these couple of cells, a couple of pixels within an image in a different representation, in a very compact representation in which I can feed, for example, to a machine learning algorithm that can learn easily and fast, in a very efficient way, okay? And that's the beauty of histogram of oriented gradient. It's kind of, you're applying you are zipping a file in a way. You're getting your file, you are zipping it. You're just removing all the unnecessary information, okay? Condensing down a lot of information from, let's say, 64 by 64, you're condensing it down to, let's say, 9 values, in a way, okay? And that 9 values just represents all the features within the image. It's really powerful, and I'm really kind of more, I think you guys can feel it, just I'm a little bit passionate about that topic. It's very interesting, and it can show you after how can we actually train a machine learning classifier to detect objects using the histogram of oriented gradients, okay? So let's assume that I zoomed in within that pixel, as you guys can see here, and that's pretty much my pixel, okay? That's kind of my zone, that's my area. So what the pixel under consideration is this pixel, and I'm looking at the pixels around it per se. So here I have 100, 120, 50, and 70. So how can I calculate the gradient in the x direction? What I could do is I could simply subtract. I'm moving this way, so I'm going to subtract 120 minus 70, right? And that will be the gradient value within the x direction, which is 120 minus 70, which is equal 50. Okay, all right? Okay. The next step is I'm going to check the gradient in the y direction. I'm going from 100, okay? Again, I'm going to 50, let's say to 100. So I'm going to go, okay, 100 minus 50, that will give me again 50, all right? Let's put it all together. Then I have pretty much kind of a vector that tells me, okay, that's my gradient in the x direction and in the y direction. So now I have a gradient 50 in the x and 50 in the y, all right? Once I have these two pieces of information, actually I can just a little bit go back to the other mathematics that I discussed before. I can get the overall gradient value or gradient magnitude and gradient angle, if you guys recall before. So I can get the square root of 50 square plus 50 square, or kind of gradient x square plus gradient y square under the square root will give me 70. And then I can get the gradient angle too, which is, indicating there is a 45 degrees. And that's the beauty of it. Now we can represent, instead of having gradient separately in the x direction, gradient separately information in the y direction, I mix them together and I got magnitude and direction too, which kind of a vector. And that's where the histogram of kind of oriented gradients, you're looking at gradients in a kind of orientation. What angle are you looking for, okay? So here, simply put, I can represent these couple of pixels in a way, in a kind of, like a magnitude indicating the length of my arrow. If that arrow is long, that means there's a higher magnitude value. If it's a little bit short, that means maybe like 20 or maybe 10 value. And then I can indicate direction too. Now I have 45 degrees, which indicating I have 45 degrees, which is perfect. That's amazing. All right. Again, I didn't get like what I'm gonna do with this, okay? Moving forward. First, that's how I obtain the oriented gradient parts. Now I have gradients that has been oriented, which is different angles. Let's get the histogram of it. And that's, again, another fascinating idea. So how can we do this? Let's assume, again, let's take a look at a practical example. Let's assume I have my truck. First step, if I'm going to use, let's say, I have to define, when I calculate the histogram of oriented gradient, I have to identify kind of a zone or a cell, we call it cell area. In this area, I'm going to be representing it by kind of the, by a HOG feature, or histogram of oriented gradient feature, okay? So using 8x8 pixel, I'm going to compute gradient and magnitude direction, all right? So simply put, I'm going to take the image, I'm going to get gradient, that's gradient x, that's Sobel x, okay? I'm going to get Sobel y, if you guys can see the derivative, it's kind of, like vertical, so that's Sobel y, or gradient in direction y. And then afterwards, what I'm going to do is I'm going to mix them together. I'm going to get the gradient in the x direction, gradient in the y direction. So for each pixel, now I have gradient in the x, gradient in the y, right? Perfect. Next step, I'm going to calculate the magnitude, gradient magnitude and direction. Again, square root, gx squared plus gy squared, and tan minus 1, gy divided by gx will give me the angle, and will give me the magnitude value as well. So I have the magnitude and I have the direction. All right, great. So now, pretty much, I have for each pixel, I have a value which indicating the length of that line, and I have an angle or orientation, okay? So the beauty about the histogram of oriented gradient is that I can take the oriented gradients that I have and can kind of draw a histogram of it, the distribution of it in a way, okay? Which is, simply put, how many, for example, gradients within that cell that has 45-degree angle. And that's where I'm going to draw my histogram of oriented gradient per se. And that's the beauty of it. So that's kind of the orientations, which is, I'm going to divide simply the 180 degrees to, let's say, from 0 to 20, from 20 to 40, and so on and so forth. And here I'm going to plot all the gradient values or gradient orientation magnitudes. Here I'm showing magnitudes, here I'm showing values. And that's the amazing part of it. Now I can put all the information within that pixels, within, let's say, the 8x8, which is 64. I can simply kind of combine them or zip them in a way, kind of, again, as you obtain like a zip file, okay, compress them in a way to obtain these kind of values, which is, again, what we call histogram of oriented gradient. Okay, in another fashion, I can even view all these pixels within all that range, within all these cells, but kind of, you know, this format, which is, okay, showing, okay, at different angles, I have different magnitudes. That's the magnitude for, let's say, the specific angle. This is the magnitude at 0 angle. This is magnitude at 90 angle degrees, and so on and so forth. And that's the beauty of it. Now you condense all the image in kind of these, like, you know, like image in a way, in a very kind of, you know, a compressed form, that you simply reduce 64 vectors into kind of just 9 values, which is the beauty of the what we call histogram of oriented gradients. All right? Okay. Sounds great. So let's take again a little bit more look. I know it's sometimes a little bit confusing. So let's take a look at what does a HOG feature look like. Actually, that's what a HOG feature is going to look like. That's a truck. That's how basically computers or, you know, machine learning algorithm, like a support vector machine, we're gonna know a truck. Okay. So we humans, we can detect, okay, this is a truck, okay, using just, you know, different colors, different features, and that's the HOG features. That's how you can compress all the information using these kind of, you know, like stars, you know, white stars in a way, and that's the HOG features. And that's how can you choose or take all this basic information, feed it in a classifier to detect if you see a truck or no. Okay. All right, that's great. Again, I know it's a little bit confusing. Let's see what can we expect. Again, so we're gonna take again a window, kind of like a we'll call it cell. In each of the cells, we're gonna come up with this kind of star value, indicating different gradients, magnitudes, and different angles. We're gonna again shift again. We're gonna get another feature, HOG feature. Shift again, get another HOG feature. So these are the dimensions of what we call the cell, which is very important. And that's kind of, you know, what we're gonna be getting out of it. Okay, so again, to summarize, HOG features are a kind of a feature descriptor used for object detection. HOG feature is very powerful because it can be used and coupled with what we call a support vector machines classifier, which is a machine learning algorithm that can classify objects for us. HOG applies, again, a sliding window detector over an image, and a HOG descriptor is computed for each position. And again, HOG takes care of the scaling issues by changing image scale, pyramiding. I can actually scale it down, like scaling up and down, so I don't have to worry about the different scaling within the image. And again, obviously, it's not dependent on the color. It's not dependent. It's very, very, very powerful and very compact way of representing images. All right. I hope it wasn't too difficult, and I hope you guys enjoyed it. And let's see how can we apply HOG features in the next exercise. I hope you guys enjoyed it, and see you in the next section.